So, hello, welcome back to this series of lectures on numerical optimization. So, in the last class, we were looking at convex sets, and the convex sets are defined as those subsets of Rn, where if you take a line segment in a set, the line segment joining any 2 points of that set entirely lies within the set. For example, suppose we take a set like this. So, this set is a convex set, because if we take any line joining the 2 points, that lies entirely within the set. On the other hand, suppose we take a, so this set is convex. On the other hand, if we take a set like this, where we do not include the interior of the set, then such a set is not convex. Okay, so it is important that the line segment joining any 2 points should lie entirely within the set. For example, in the set on the right side, if you take a line joining these 2 points, you will see that only these 2 points, the end points of that line segment lie within the set, while the interior of that line segment does not lie within the set. So it is important that any line segment joining any 2 points of the set should lie entirely within the set. So, for example, so if we take a set like this, and so we see that this set is not convex, because if we take a line segment joining these 2 points, that does not lie within the set. But we also saw that there are some ways to convexify a set, what that is called the convex hull of a set. So, for example, if we consider this set which is not convex, now that set can be made convex by suppose we draw a line like this and then include the entire portion. Now, the new set which is formed, now that becomes a convex set, right. So, the convex hull of a non-convex set is a convex set. So, in other words, the convex hull is a set which is the smallest convex set which contains the given set. So, we were looking at the definition of a convex hull, and we saw that the convex hull of a set is the intersection of all convex sets which contain the set S, and we are going to denote it by the symbol convex hull of the set. Now, by the definition of this convex hull, it is a convex hull is a convex set, because we are taking the intersection of all convex sets. And that is why it is a, we saw this result in the last class, that the intersection of any collection of convex sets is a convex set. And some examples of convex sets that we saw in the last class were that if you are given 2 points. So, if we are given 2 points, the convex hull of these 2 points is a line segment joining these 2 points. Now, if you are given a set in a 2-dimensional space which is like this, then the convex hull of this set is the set of all points which are on or above this curve. So, this becomes a convex hull of the set. So, we saw this in the last class. Now, in today's class, we are going to look at some of the properties associated with this convex sets, which could be used in deriving the optimality conditions of a nonlinear or a linear programming problem. So, let us first look at a theorem. So, we will call it as a theorem CS1. So, suppose S is a non-empty and a closed convex set in Rn. and let us consider a vector y or a point y which is not in the set S. So, remember that S is a non-empty and closed convex sets. Then the claim is that there exists a unique point x naught which has a x naught belonging to S which has a minimum distance from y, and then further x0 is the minimizing point if and only if the condition y minus x naught transpose x minus x naught less than or equal to holds for all x in the set S. So, we will see this first the interpretation of this result. So, suppose we have a set S which is a non-empty closed convex set in R n, and let us consider a point y which is not in the set S. So, the theorem says that there exists a point x naught in the set S which has a minimum or the least distance from the set y, and not only that there exists a unique point, not only that there exists a point, but that point is also unique. So, you cannot find any other point in the set S which is at the same distance as the distance between y and x naught is. Okay. So, this is a very important point that needs to be noted. And further, if we take that point x0 and take any point x in the set S, and if you take the two vectors y minus x0 and x minus x0, the dot product of those two vectors is non-negative, which means that they make an obtuse angle with each other. So, we are going to see the proof of this theorem now. Okay. So, given the set S and the point which is a point y which is not in the set S, we will give a proof sketch. It is very easy to write the proof. So, we will give some important points that need to be considered while writing the proof. So, we are given a set S which is a subset of R n, and it is a closed convex set, and y is not in S. Now, the first thing that we have to show is that there exists a minimizing point in S that is closest to y. Okay. So, how do we show that there exists a minimizing point? So, what we are interested in is that we are interested in finding out a point x in S such that the distance between x and y is the least. Remember that I have written here infimum because we do not know whether such a point x exists in the set S. So, that is why we have written the infimum here. So, let this infimum of norm of x minus y with respect to x belonging to S be denoted by delta. So, delta is going to be this distance between x minus y. We still do not know whether such a x belongs to S exists or not. Okay. Now, let us look at this function norm x minus y. Now, norm x minus y as a function of x, it is a continuous function. So, we are trying to minimize a continuous function. Now, look at the set S. We have just said that the set S is closed convex set. Okay. Now, if you recall Weierstrass theorem says that if you want to minimize a continuous function over a closed bounded set, then the minimum and maximum exists in the set S. Now, the set S which is given to us is closed, but it is not necessarily bounded. Okay. And that is why we cannot use Weierstrass theorem directly to solve this problem. Although f is a continuous, the function norm x minus y is continuous, the set S is not bounded. So, we cannot directly use Weierstrass theorem. So, we have to modify this problem a little bit, so that we try to minimize this function, continuous function over a bounded set. Now, to do that, what we do is that let us assume that delta is the infimum, and what we do is that around y, taking y as the center, we consider a ball of radius 2 delta centered at y. Remember that this is a closed ball, but I have not shown it in the figure to avoid the clutter in the figure. So, this closed ball basically is the boundary of the ball is shown, and as well as the interior of the ball, that is the closed ball. So, now suppose if we consider the set S intersection the closed ball of radius 2 delta centered around y. Now, this ball is a closed ball, S is a closed set. Now, this ball is a bounded set. Now, intersection of that ball with respect to S is a bounded set. So, intersection of two closed bounded sets will give us a closed bounded set. So, it is this set that we are talking about, the intersection of S and then the closed ball. So, it is this part that we are talking about. Okay. Now, we can use Weierstrass theorem, because now we have a function norm x minus y, which is a continuous function in x, and the constraint set that we are talking about is closed and bounded. So, by Weierstrass theorem, there exists a minimizing point x0 in S that is closest to y. So, this point x0 is shown here. So, this is closest to y, and x0 can be written as the argmin of norm of x minus y, where x belongs to now S intersection b y comma 2 delta. So, that is the ball of radius 2 delta centered around y. So, such a x naught exists now by using Weierstrass theorem. So, what we have shown so far is that there exists a minimizing point in the set S that is closest to y. Now, what is the guarantee that this point is a unique minimizing point? So, let us look at the how to show the uniqueness of this minimum point. So, the idea is to use the triangle inequality. So, let us assume that there exists some x naught which belongs to S such that y minus the distance between y and x naught and the distance between y and x hat is same as delta. Right. And then what we have to do is that we have to show that if such a thing happens, then we may end up in a contradiction. So, the only thing that this is possible, the only way this is possible is that x0 coincides with x hat. Now, to do this, we have to use a triangle inequality. So, now since S is a convex set that is given to us, the convex combination of x0 and x hat always lies in the set S. So, we have lambda 1 x naught plus lambda 2 x hat always belongs to the set S when lambda 1 and lambda 2 are non-negative and lambda 1 plus lambda 2 is 1, and in this case they are that is true. So, we take this point and then use the triangle inequality. So, if we use the triangle inequality, what we get is the distance between y and x naught plus x hat by 2 is less than or equal to the distance between y minus y and x naught and the distance between y and x hat. Now, we know that the distance between y and x naught is same as distance between y and x hat, which is delta. So, this the right hand side becomes 2 delta. So, what we have is that norm of y minus x naught plus x hat by 2 is less than or equal to delta. Now, if norm of y minus x naught plus x hat by 2 is strictly less than delta, then we get a contradiction, because we have proved that x naught is a minimizing point. So, if we find another point which is at a distance from y, which is at a distance less than delta from y, then we get a contradiction. So, the equality here holds. So, which means that norm of y minus x naught plus x hat by 2 is equal to delta. So, which means that x naught and x hat should coincide. So, if the stint inequality holds, we get a contradiction. Okay. So far we have shown that there exists a unique minimizing point in the set S which is closest to y. Now, we will prove the remaining part of the theorem. Now, what we have to show is that if x naught 0 is the unique minimizing point if and only if y minus x naught transpose x minus x naught is less than or equal to 0 for all x belongs to S. Okay. So, let us remember that we have to show if and only if. So, we have to show it both ways. So, let us assume that some x belongs to S and the inequality y minus x naught transpose x minus x naught less than or equal to 0 holds. Okay. And then we have to show that x naught, in such a case x naught is indeed the unique minimizing point. Now, how do we show that? So, let us take any x belongs to S and then try to find the distance of x from y, and we have to show that norm of y minus x square is greater than or equal to norm of y minus x naught square for all x belongs to the set S. So, we have to introduce x naught in this equation. So, we write norm of y minus x square as y minus x naught plus x naught minus x square, norm of y minus x naught plus x naught minus x square. Now, we expand this the right side. Now, if you expand the right side, so the square of the first term plus the square of the second term, the square of the norm of the second term, and then 2 into the inner product of the two vectors. So, this is what is shown here. Now, so if you look at the second term, so x naught is a point which is in the set S, and x is also in the set S. Now, norm of x naught minus x square is always a non-negative quantity. Now, if you look at the third quantity, the inner product of y minus x naught and x naught minus x is always greater than or equal to 0 because of this. Remember that here we have used x minus x naught and here we have used x naught minus x. So, the third term is always greater than or equal to 0. So, these two terms are always greater than or equal to 0. So, which mean that norm of y minus x naught square is greater than or equal to y minus x naught norm of y minus x naught square for all x belongs to the set S, and which means that x0 is the unique minimizing point for the is the unique minimizing point from y. Okay. Now, we prove the other way. So, now we assume that x0 is the unique minimizing point and show that this condition holds. Okay. Now, x0 is the unique minimizing point from y, means that the norm of y minus x naught square is less than or equal to y minus z square for all z belongs to S, because x0 is the closest point in the set S from y. Right. Now, we use the convexity of the set S. Now, since set S is convex, if we take any x in the set S, I can say that lambda x plus 1 minus lambda x naught always belongs to the set S for all lambda in the closed interval 0 to 1. So, we can always say that for any x in the set S, x0 always in the set S. So, the line segment joining those x and x naught always lies in the set. Now, we use this point and substitute it here. So, what do we get? So, we get that norm of y minus x naught square is less than or equal to y minus x naught minus lambda into x minus x naught square. So, we have just substituted this quantity here and rearranged the terms so that we could write it as y minus x naught minus lambda into x minus x naught. Now, let us try to expand this. Now, if you expand this, the right side, what do we get? So, the what we get is that norm of y minus x naught square plus lambda square norm of x minus x naught square minus 2 lambda y minus x naught transpose x minus lambda. Now, these two quantities are the same. So, they get cancelled, and suppose if you bring in the third quantity on the left side and divide by lambda, assuming that lambda is non-zero, then what we get is 2 into y minus x naught transpose x minus x naught is less than or equal to lambda norm of x minus x naught square. So, now if we take limits, so letting lambda tending to 0, what we get is that y minus x naught transpose x minus x naught is less than or equal to 0. So, we get the result that if x0 is the minimizing point, then y minus x naught transpose x minus x naught has to be less than or equal to 0. Now, geometrically, what we have shown here is that given a set S and a point x not, and a point y which is not in the set S, then the first thing that we showed is that there exists a point x0 in the set S which is at a least distance or minimum distance from y, and that point is the point x0. Now, we also showed that such a point x0 is always unique. Then we showed that if x0 is the minimizing point, then y minus x naught transpose x minus x naught less than or equal to 0, and if y minus x naught transpose x minus x naught less than or equal to 0 for all x belongs to S, then x0 is the minimizing point. And it is easy to see it here. Now, if we consider the vector y minus x naught, okay, and then take any x in the set S and take the vector x minus x0, you will see that the vector y minus x0 always makes an obtuse angle with the vector x minus x0. So, this is the interpretation of this result. Now if we take a hyperplane which is perpendicular, whose normal is the vector y minus x naught. So, that hyperplane at x naught is shown here. Now, you will see that this this point, the point y lies in one half space of that hyperplane, and then the entire set lies in another half space of that hyperplane. So, in some sense the hyperplane that we have shown here is trying to separate the set S and the point y which is not in the set S. So, we will see more about this separating hyperplane now. So, let us consider two non-empty subsets in Rn. Let us call them as S1 and S2, and let H be a hyperplane is a set of which is a set of points x such that A transpose x equal to B. So, we saw in the last class that A is normal to the hyperplane. Now, the hyperplane H is said to separate S1 and S2 if A transpose x is greater than or equal to B for all x in S1 and A transpose x less than or equal to B for all x in S2. So, very soon we will give the geometrical interpretation of these results. Now, if the inequality in the definition is strict, then we say that the hyperplane H is said to strictly separate the sets S1 and S2. So, notice the difference between the two definitions, that here the inequality is not strict. So, A transpose x is greater than or equal to B for all x in S1 here, and A transpose x less than or equal to B for all x in S2, while here the inequality is strict. Now, there is another notion which is called the strong separation. So, we said that the hyperplane H is said to strongly separate S1 and S2 if A transpose x is greater than or equal to B plus epsilon for all x in S1 and A transpose x less than or equal to B for all x in S2, where epsilon is a positive scalar. Okay, so, we will see the meaning of these definitions. So, let us consider the two sets S1 and S2. These S1 and S2, they are touching each other. Okay, so, there exists a point which is common to both the sets S1 and S2. Now, this is now if we draw a hyperplane H which is like this passing through that point which is in the intersection of S1 and S2, you will see that in one half space of this hyperplane the set S1 lies. Of course, I am talking about the closed half space, and in the other closed half space the set S2 lies. Okay, so, such a hyperplane is called the separating hyperplane. So, there exists one point which is the intersection of these two sets S1 and S2 through which this hyperplane passes. Now, let us modify the sets S1 and S2 as open sets. So, that is why the boundary of these two sets are shown by dotted lines. Now, they do not have any intersection. So, if I take the same hyperplane, now we can say that it strictly separates S1 and S2. So, that means that if I take any x from S1 we can say that A transpose X is strictly greater than B for all x in S1, and similarly A transpose X is strictly less than B for all x in S2. So, such a hyperplane H, which is the set of all x such that A transpose X equal to B, is said to strictly separate S1 and S2. So far we have studied what are separating hyperplanes, what are strictly separating hyperplanes. Now, what can we say about strongly separating hyperplane? Now, here is an example of a strongly separating hyperplane. So, you will see that we have sets S1 and S2, which are away from each other. They do not have anything in common. Even the boundaries do not touch each other. Then, in such a case, we say that H strongly separates S1 and S2. So, which means that A transpose X is greater than or equal to B plus epsilon, where epsilon is some positive scalar for all x in S1, and A transpose X less than or equal to B for all x in S2. So, you will see that this hyperplane H is a strongly separating hyperplane. Okay. Now, with this notation, we will now see the result, which discusses about the separation of a closed convex set and a point. Now, suppose that S is a non-empty closed convex set in Rn, and let us take a point y which is not in the set S. Then there exists a non-zero vector A and a scalar B such that A transpose y is greater than B and A transpose X less than or equal to B. So, which means that there exists a hyperplane which separates a non-empty closed convex set from a point y which is not in the set S. So, we have seen this figure earlier. So, we have a set S which is non-empty and closed and convex, and we have a point y which is not in the set S. Then the claim is that there exists a non-zero vector A and a scalar B such that A transpose y is greater than B, or in other words, there exists a hyperplane which separates the two sets, and we can easily see that this is the this is one hyperplane which separates y and S. So, for so if you take a vector A as y minus x naught, okay, and then choose B appropriately, then what we get is a hyperplane passing through x naught whose normal is y minus x naught, and that clearly separates y and the set S. So, the proof for this is very easy. By the theorem CS1, we know that there exists a unique minimizing point x naught in such that x minus x naught transpose y minus x naught is less than or equal to 0. So, the idea is that we choose y minus x naught as A and A transpose x naught as B, and so we have chosen y minus x naught as the vector A and A transpose x naught as B. Then we get that A transpose x is less than or equal to B for all x in the set S, and A transpose is nothing but y x naught transpose y minus x naught, and since y is not equal to x naught, because y is a point which is not in the set X. So, this quantity is always positive quantity. So, what we get is A transpose y greater than B. So, hence the result follows. So, if we are given a non-empty closed convex set in Rn and y is as a point not in S, then it is always possible to construct a hyperplane which separates the set S and the point y. Now, let us look at the definition of cone. Set K, which is a subset of Rn, is called a cone if you take any vector x in the set K and a scalar lambda which is non-negative, then we have lambda x belongs to the set K. And one more definition about the convex cone. So, K is a convex cone if it is both convex and it is a cone. So, first of all, it has to be a cone. So, which means that it should satisfy this definition. So, what this definition essentially means is that if you take any vector x in the cone, then a non-negative multiple of that vector should always belong to the cone. Now, remember that lambda is greater than or equal to 0. So, when you substitute lambda equal to 0, which means that 0 also should belong to the cone. So, the origin, so in this course we will use the notation for the cone that the origin always belongs to the cone. Now, if we have a cone and if that is a convex set, then we call that as that set as a convex cone. Now, we will see some examples of cones. So, on the left side you will see a line passing through the origin. Now, this is a cone, because if you take any vector on this in this set and take a non-negative multiple of that vector, that always belongs to the set. So, if I take a vector here and take a non-negative multiple of this, so it would lie along that ray starting from the origin. On the other hand, if I take a vector in this direction and take a non-negative multiple of that, it will lie along the ray. So, this is a cone. Similarly, this is a cone. So, if we take any point in this on these arms of this cone as well as in the shaded region and take that vector and take a non-negative multiple of that vector, that always lies in this set. So, this is an example, these are some examples of cones. Now, here are some more examples. So, in the first example, what we have done is that we have added another line passing through the origin. Now, this also remains a cone, because by the definition of cone, any non-negative multiple of any vector in that set always lies in the set. So, this is a cone. Similarly, this is also a cone. We have just added one extra ray to the previously seen cone. So, any vector on in this direction, if you take a non-negative multiple of that, that always lies in this set, right. But the difference between the two examples shown earlier and the two examples which are shown here is that these cones are convex, while these cones are not convex. Okay. Now, we will look at an important result which is useful in deriving some of the optimality conditions that we are going to study later in the course, and that result is called Farkas Lemma. So, both Farkas Lemma and its corollary, they are very important in deriving optimality conditions for linear or nonlinear programming problems. So, let us first give the statement of the lemma. So, suppose A is a m by n matrix of real numbers and C is a vector in n dimensional space. Then Farkas Lemma states that exactly one of the systems has a solution, and what are those two systems? So, one is the set of all x such that x less than or equal to x less than or equal to 0, C transpose x greater than 0 for some x in Rn, and the other one is A transpose y equal to C, y greater than or equal to 0 for some y in Rn. Now, before we prove this lemma, let us look at the geometrical interpretation of this. Okay, so let us consider n dimensional vectors, and let us denote them by a1, a2, am. Now, define a matrix A where the vectors the m vectors are stacked row wise. So, the first row contains a1 transpose, the second row contains a2 transpose, and so on. Okay. Now, suppose for example, if we take 3 vectors a1, a2 and a3. Okay, so, we can stack them in the matrix A. Now, if you look at Farkas Lemma, so what we are interested in is the first system says Ax less than or equal to 0, C transpose x greater than 0. Okay. So, the first thing in the system 1 is that the set of all points x such that Ax less than or equal to 0. Now, since we have stacked the vectors a1, a2, a3 in the matrix A row wise, so what we are interested in is the set of all x such that A1 transpose X is less than or equal to 0, A2 transpose X less than or equal to 0 and A3 transpose X less than or equal to 0. So, A1 transpose X less than or equal to 0 is the set of all vectors X which do not make an acute angle with the vector A1. Okay. So, if we draw in 2-dimensional space, if we draw perpendicular vector to A1, so one is this and the other one is this. So, these are the perpendicular vectors, and then collect all the vectors collect all the vectors which make an obtuse angle with A1 and right or obtuse angle with A1. So, that becomes a half space. Now, we do the similar exercise for A2 and A3 and take the intersection of those half spaces. So, the intersection of those half spaces if we take, finally what we get is something like this. So, this is the set of the shaded region including the points on the arms of this cone. They form the set X such that Ax less than or equal to 0. So, all the points or all the vectors in this shaded region, they do not make an acute angle with any of the vectors A1, A2 and A3. Okay. So, this was the first half of the system 1. Now, the other half says that C transpose X greater than 0. Now, let us assume that the vector C is like this. So, since C is pointing like this, so C transpose X equal to 0 is the hyperplane which is shown here with a dotted line, and this part of the half space shows C transpose X greater than 0. So, if we intersect the previously seen cone which was contained in the two arms, the red colored arms, and intersect that with the set where C transpose X is greater than 0. So, remember that now we are talking about the open half space, not the closed half space. This is the open half space formed by the hyperplane C transpose X equal to 0. So, if you intersect them, so it gives us this intersection which is shown here. Now, what Farkas Lemma says is that either the system Ax less than or equal to 0 and C transpose X than 0 for some x greater than for some x in Rn, either that has a solution, or if that does not have a solution, then we can write C as a non-negative linear combination of Ai. So, C can be written as sigma yi Ai, where yi's are greater than or equal to 0. So, either Ax less than or equal to 0 and C transpose X greater than 0 for some x in Rn, or A transpose y equal to C and y greater than or equal to 0 for some y in Rm. So, that means that either you find x which satisfies this, and if you cannot do that, then there exists some y such that we can write A transpose y equal to C and y equal to 0. So, this is a very important lemma, and we are now going to see the proof of this lemma. Okay. Now, what we have to show is that either of the two systems given here have a solution and not both. So, suppose if system 2 has a solution, then we have to show that system 1 does not have a solution, and suppose system 2 does not have a solution, then we have to show that system 1 has a solution. Okay. So, let us assume that system 2 has a solution. So, system 2 has a solution means that there exists some y in Rm such that A transpose y equal to C and y greater than or equal to 0. So, there exists some non-negative y such that C can be written as A transpose y. Okay. Now, let us assume that there exists or let us take some x such that Ax is less than or equal to 0, and then let us see what happens to C transpose X. So, let us take some x in Rn such that Ax less than or equal to 0, and what we are interested in finding out what happens to the dot product of C and X. So, if we take C transpose X, Now, C transpose x is nothing but y transpose Ax, okay. And we know that Ax is less than or equal to 0 and y is greater than or equal to 0. So, y transpose Ax is less than or equal to 0. So, if we consider any x such that Ax is less than or equal to 0, then definitely C transpose x has to be less than or equal to 0. So, which means that we cannot find x where Ax is less than or equal to 0 and C transpose x greater than 0. So, which means that system 1 has no solution. Now, let us look at the other part of the proof. So far we studied that if system 1 has a solution, then system 2 has a solution, then system 1 has no solution. Now, let us consider the remaining part where system 2 has no solution. So, that means that C cannot be written as non-negative linear combination of AS, or C cannot be written as A transpose y equal to C, where y is greater than or equal to 0. So, let us assume that let us collect all such x's such that x can be written as a non-negative linear combination of the vectors, the rows of the matrix A, or x can be written as A transpose y, where y is non-negative. Now, clearly S is a closed set and also a convex set, intersection of closed convex sets is a closed convex set. And then since system 2 does not have a solution, C certainly does not belong to the set S. Okay. Now, what we have to do is that we have to now prove that there exists some vector x in n-dimensional space such that x is less than or equal to 0 and C transpose x is greater than 0. Okay. Now we have a closed convex set and a point C which is not in the set S. So, we can use the previously studied theorem to show that there exists some vector P in Rn and alpha in R such that P transpose x less than or equal to alpha for all x belongs to S and C transpose P greater than alpha. That means that there exists a hyperplane set of all x such that P transpose x equal to alpha, which separates the convex set and the point C which is not in the that closed convex set. Okay. Now, if you look at the definition of S, y is greater than or equal to 0. So, when y equal to 0, x becomes 0. So, that means that the origin always belongs to the set S. Now, if you look at this inequality, P transpose x less than or equal to alpha for all x belongs to S. Now, since origin belongs to S, if I substitute x equal to 0 here, what do we get is that alpha greater than or equal to 0, right. So, alpha is greater than or equal to 0 since the origin always belongs to the set, and since alpha is greater than or equal to 0 and C transpose P greater than alpha, so C transpose P is always greater than 0. So, now what we do is that we will study the relationship between alpha and P transpose A transpose y. Now, alpha is always greater than or equal to P transpose A y, because any x can be x in S can be written as A transpose y. So, alpha is greater than or equal to P transpose x. So, which means that alpha is greater than or equal to P transpose A transpose y. Now, reversing the order, we can write this as y transpose AP. This is true for all y greater than or equal to 0. Now, remember that y is greater than or equal to 0. So, we can make y very, very large. It is possible to do that. Now, if that happens, then if AP is also greater than or equal to 0, suppose AP is greater than 0, then y is very large, then y transpose AP will become a very large quantity, and we want alpha to be greater than or equal to y transpose AP, and that may not be possible if y is made very, very large. So, the only way that this inequality holds is that AP has to be less than or equal to 0, since y can be made arbitrarily large. So we are able to get a vector P in Rn such that AP is less than or equal to 0 and C transpose P is greater than 0. So, which means that the system 1 has a solution. So, there exists a P in Rn such that AP less than or equal to 0 and C transpose P greater than 0. So, which implies that system 1 has a solution. So, either of these two things happen, either if you are given a matrix A, so one can treat the rows of the matrix A as the vectors A1 to Am and the vector C in Rn. Then if we consider the system x less than or equal to 0 and C transpose x greater than 0, if that does not have a solution, then the vector C can be written as a non-negative linear combination of the rows of the matrix A. Okay. So, this is a very important result which will be useful, and there is a corollary to that result, and that we will see now. So, just recall the Farkas lemma where we had matrix A and the vector C, and either of these two systems has a solution. Now, the corollary says that if we are given a m by n matrix, then exactly one of the systems has a solution. So, either Ax is less than 0 for some x in Rn, or A transpose y equal to 0 and y non-negative for some non-zero y in Rn. So, remember that now y is non-zero means that all the elements of y cannot be 0 at the same time. So, now this corollary does not use the vector C that we have used earlier. Now, it is if we look at the two systems, the one given in Farkas lemma and the one given in the corollary, you will see that there is some similarity between the two. Now, here we had Ax less than or equal to 0, while here we have Ax less than 0. Now, C transpose x greater than 0 is not there here, and similarly A transpose y equal to 0, here we had A transpose y equal to C and y non-negative for some non-zero. So, if we can put this system of two systems of equations in the form like this, then one can use Farkas lemma to prove the corollary. So, let us see how to put that in the form of Farkas lemma. Okay. Now, this is the first system in the corollary, Ax less than 0 for some x in Rn. Now, we can write this as, so we can add some variable, we can take some constant z which is a positive constant, and take a vector E. E is a vector, m dimensional vector of all ones. So, we can write Ax less than 0 as Ax plus Zd less than or equal to 0 for some x in Rn and z greater than 0. So, now this is now we can combine the vectors x and E to form a new vector, and we can write the we can combine x and z to form a new vector and write a new write the same system in this form, A E into x z less than or equal to 0. So, now you will see that suppose we call this matrix as A tilde and this x z as x tilde. So, we have A tilde x tilde less than or equal to 0, and let us call this vector, the row vector, as C transpose x tilde greater than 0. So, now you will see that this is in the same form as the system 1 given in Farkas lemma, with the definition of x is now x appended by z, and the definition of E is nothing but A appended by the vector E. So, now system 2 also can using that same notation, we can write the system 2 as this, which in turn can be written as A transpose y is equal to 0, E transpose y equal to 1 and y greater than or equal to 0. So, the only thing that we have added in system 2 is E transpose y equal to 1, because A transpose y equal to 0 and y greater than or equal to 0 was always there. right. So, the system 2 is of the form A tilde y equal to C y greater than or equal to 0. Okay. So, now the only thing that we have extra here is that E transpose y equal to 1. So, if using Farkas Lemma, if suppose there exists the system 2 has a solution and we get y such that A transpose y equal to C and y greater than or equal to 0, we can always normalize that y to make sure that E transpose y equal to 1. Okay. So, now this is of the same form as what we wanted in Farkas Lemma. So, the corollary can be easily proved by just rearranging the terms. Okay. Now, let us look at the supporting hyperplane. So, suppose f S is a non-empty subset of Rn and x0 is a boundary point of the set S, then the hyperplane H where A is a normal to the hyperplane and that is passing through the point x0 is called a supporting hyperplane of S at x. So, that means that the set S entirely lies in one of the closed half spaces of the hyperplane H. So, either lies in H plus or H minus. Now, here are some examples. So, on the left side you will see that the set S is given and x0 is the boundary point of S. Then there exists a hyperplane such that the entire set S lies in one closed half space of this hyperplane. Now, similarly, you can see that this is another supporting hyperplane for the same set S. Now, you will see that it is touching the set at the 2 points. Now, if you take this point, we cannot draw a hyperplane which supports the set S, because any hyperplane passing through this will intersect the set S and the set S will not entirely lie in the one of the closed half spaces. So, for such points it is very difficult to construct a supporting hyperplane, but we have a result which says that if S is a convex set, then there exists a supporting hyperplane at every boundary point of the set S. So, we have this theorem which says that if S is a non-empty convex set in Rn and x0 is a boundary point of S, then there exists a hyperplane that supports S at x0. Okay. Now, we will see one more result, that suppose S1 and S2 are two non-empty disjoint convex sets in Rn, then there exists a hyperplane that separates S1 and S2. So, we will see the proof of this. Now, we know that if we are given a convex set S and a point which is not in the convex set, right, then there exists a hyperplane that separates the convex set from that point. Now, here we are given two non-empty disjoint convex sets. Now, can we combine them to form a convex set and use that to prove this? So, let us see how to do that. So, let us consider a set S which is S1 minus S2. So, which is basically the set of all x1 minus x2 such that x1 belongs to S1 and x2 belongs to S2. Now, this set is a convex set. One can easily prove that. Now, further the origin does not belong to the set, because we have disjoint convex sets. So, they do not have any intersection. The origin does not belong to the set S. So, now we have a convex set S and the point which is not in that convex set, point origin which is not in that convex set. So, there exists a, by the earlier seen result, there exists a hyperplane that separates S and the origin. So, there exists a vector A such that A transpose x is less than or equal to 0 for all x belongs to S. So, now if we replace x by x1 minus x2, what we get is that A transpose x1 is less than or equal to A transpose x2 for all x in S1 and x2 in S2. So, that means that there exists a hyperplane that separates the two sets S1 and S2. Now, under what conditions that this hyperplane will strictly separate S1 and S2. So, I will leave it as an exercise to you to find out the conditions under which for a given two non-empty disjoint convex sets, there exists a hyperplane that strictly separates S1 and S2. So, this completes our discussion on the convex sets, and as we will see in the next class that these convex sets will be used in defining what are called convex functions, and convex functions, minimization of a convex function with respect to a convex set is called a convex programming problem, and that's very important in the optimization literature. So, we will study those things in the next class. Thank you.